Thanks a lot. Yeah, after sorting out this little technical difficulties and finally getting a mic, and I hope everybody can hear me. All right. My name is actually Kai Kunze. I'm a PhD candidate from the Embedded Systems Lab at the University of Passau, supervised by Professor Paul Lukowitz. And in the next 40 to 50 minutes, we will, take a closer look at the state-of-the-art in wearable computing. To get us started and give you a little bit a common background or common ground to start from some motivational slides. As I guess everybody of you knows, currently today we are in a state where computing is embedded more or less in all kinds of everyday devices. So your watch, your phone, your gaming console, car, washing machine, and so on. Although the I have already, so I'm fine.
Okay, but talk.
Okay. Basically, computing is embedded in everyday devices and everyday artifacts and objects, and we think that it should support us, in everyday life with our tasks, with our things we need to do. However, usually it looks more like this. This is actually in the background. There's an unstaged picture of my desk at the University of Passau, so of our office, and so basically. The devices we use today don't really support us in our everyday life. They more or less disturb us. And if we have this embedded technology, very close to us and near to us, so watch, mobile phone, and so on, the limiting factor no longer becomes, or the scarce resource no longer becomes actually processing power or memory, but user attention, so the attention of you. If the mobile phone rings, it disturbs your attention, it disturbs on what you were working on. And the vision of wearable computing, or also ubiquitous computing, pervasive computing, I tend to use them interchangeably. For me, they all kind of share the same vision. They come in different flavors. I know you can start religious wars about that, but in general, I forgot to switch on the demo. But in general, they all aim at supporting us with transparent computing, so computing we don't see, computing that is inherent, that is useful and unobtrusive as our clothes or similar. And how this is done is basically computing needs to perceive somehow the real world. So, all the chips and memory that is integrated in these everyday devices need the way to perceive us. And, how this is of course done now is using some kind of infrastructure sensors, microphone arrays, some fixed cameras, some other things, or body-worn sensors. So, in this case, for example, accelerometers or gyroscopes, and so on. And this actually brings me then also to a first demo, how this can look like. If you look at the top, you see the little a man actually moving, and what I have on my body is basically two little sensor nodes, one here and one here. It's a particle computer from the University of Karlsruhe, TECO, and what should happen is basically it recognizes if I'm waving over an accelerometer, and it should recognize if I'm sitting down. This is sometimes difficult. Difficult, please. No? Okay. Yeah, some problem with the live demo, but at least it recognizes the variance in the accelerometer. So basically, the processing is done on the chip. I'm even surprised that it currently works on this setup because I needed to use VMware and some weird other things to get it actually running on the laptop. But you see, actually, the nice thing is this was a demo implemented during a diploma thesis of Josef Neuburger. And he basically implemented all of this on the chip. So all the classification and so on is done on a small PIC chip, and I think around 64K of memory or so. So very limited device. Yeah, I thought at least I'd bring some kind of demo with me. Let me just stop the demo because I'm not sure later on it might get distracting. Okay, and continue with the presentation. Another way, another hybrid approach or also infrastructure sensor you probably already know is the Sputnik, which is also available here at the Chaos Communication Congress, the Open Beacon. Britta and Milos actually visited us at University Passau 2 years ago and also installed a system there, so we have also running a system of Sputnik in our lab. I just wanted to promote it because I really like the idea. They put out all of their layouts and all of the software in open source, and you can just basically download and profit from their experience as well. So basically now we have these sensing capabilities in our computing. So what do we want to support? Basically every high-level user activity that you can think of, and here's just some examples. So from everyday living, so you know these very mundane, very old examples of the intelligent fridge or the intelligent stove, the intelligent house, and so on, or healthcare, work and collaboration, so helping people not to endanger themselves, doing difficult tasks more or less, and of course also sport and lifestyle activities, so you know, as virtual trainers or similar. And this brings me now to a small outline of the view. So we started off with the motivation. Now we will jump into the application scenarios. I'll give some of more concrete examples there, and then we'll look at enabling technology. So you know, what do we usually use at the Embedded Systems Lab to build such demonstrators and such systems? And then I go into a bit more detail about actually my PhD work, opportunistic sensing. So I discuss some of the problems that current activity sensing or wearable computing systems actually have, and some partial solutions. And in the end, we'll finish with some general issues. Here we will basically talk about two issues. One is how usable is the stuff? You know, it's maybe nice for researchers and for geeks, but is it really usable for the everyday person? And another issue I can't get around at the Chaos Communication Congress, of course, is privacy and privacy implications. So let's start off with a little video from one of our demonstrators. This is work done by David Banach, mostly as part of the Where IT at Work project. This is a huge integrated project.
Doctors with their work in...
It started, now I stopped it again, I guess. Now it's working, okay. And this is basically a system that was designed to help a doctor doing his daily rounds. He strips on a Linux PC. This is a Belt PC from ETH Zurich, the Cubic. He wears on the one wrist an RFID scanner, on the other wrist a motion sensor, and sets up a Bluetooth headset. And basically with this he starts his rounds in the morning. and starting to visit patients. So, he walks to the patient, basically scanning the RFID tag on the wrist of the patient, and with this he triggers an event in the system, and he basically gets all the information for the patient on the system, and then can use the motion sensor on his wrist, on his other wrist, to basically scroll up and down and select the corresponding report and check the status of the patient. And there's another gesture. Okay, now I think he'll show the scrolling. Yeah, right, so this is scrolling, this is selection. And there's another gesture to basically call for an MRI or so. He can just basically do this gesture and activate the Bluetooth headset. The context recognition part was implemented from our lab, so mostly David Banach. And this is actually not a mock-up. This was actually in place for 3 weeks in a hospital in Steyr, and with a fully working system. SAP was also, or is also a partner in the WIT project, and they actually did the backend. So basically, they did the interfacing to an R3 system. So we did a test run with real doctors, real patients with this technology. So, it looks kind of maybe a little bit mundane, but if you think about it, we really pushed this out to doctors and got feedback from them. And so one of the first feedbacks we got is that, this gesture recognition with the hand kind of sounds alright, but if you use this in a doctor-patient context and you use gestures, scrolling up like this or scrolling down like this and then selecting, you run into some trouble depending on the cultural context of the people. So the next demonstrator actually used a capacitive sensor integrated in the jacket of the doctor, and he can basically scroll up and down by just moving his hand, and then selecting is then just a press and no longer a side movement. There were 2 different flavors, a bigger one integrated over here and a smaller one down here. One of the requirements we got from the doctors was actually that they have their hands free, so they don't want to touch a stylus or they don't want to touch a mouse or something similar, because they might want to interact with the patient or do some search there. So this is one application scenario in healthcare. Another one, what we will look at, is an industrial scenario. This is some recording, some sensor recording for quality assurance, reenacted from ETH students at Zurich. From Skoda assembly line. So basically, after a car is finished, what you have is usually a check if everything is all right at the end of the assembly line, this quality assurance step, and it's quite tiresome for the worker because he might forget something. You have to check each door, you have to open each door 3 times and things like that, and check that the steering is all right, check the all kinds of moving parts of the car. And so the idea is later on to support this worker so he does not forget anything. And here you just see data recording, as I said, reenacted at ETH. We work closely together with them. This was basically, most of the work was done from Thomas Stiefmeier, student at ETH, and Georg Ogres, a colleague of mine. And here you see Clemens, another PhD student from ETH, actually performing these quality assurance tasks. And you see already that the setup is a little bit different. So you see more sensors. So you see these yellow bricks, they are motion sensors. There's the norm of the velocity and the acceleration from the hands, just plotted down here. And he was wearing force-sensitive resistors sleeves on each arm, so you get the muscle activity for each arm, and you see the raw data down here. And the only thing that is actually now classified in this video is the location. So we classify if he is on the right side of the car or on the front side. This is done with an ultra-wideband localization system, the 2 tags he wears on the shoulder. And as you already see, this looks very much different than this use case in the hospital, and this is more or less also how we do our data gathering, because sometimes if you want to recognize specific tasks, like now in this case opening the truck or closing the trunk, you sometimes don't know which, and you see you have this repetitive task, so he has to push it down 3 times and so on. You don't know what to look for in the data, so you usually use you know, a more elaborate setup. My professor tends to call it Christmas tree setup, fitting to the season, because you put a lot of sensor on the test subject, and also usually use students as test subjects, so they cannot really complain at the beginning. So this is now I showed you kind of a regular or a more extensive work in industry, and now for the last application scenario, I want to take a look at more in sports and healthcare. So this is work we've been doing since 2005 or so on, trying to recognize Kung Fu movements, and here the emphasis is basically to, on the one hand, be able maybe to do a trainer, a sports trainer, that a virtual trainer that helps you do the right movements, and on the other hand, if you go to entertainment or so on, imagine you play Street Fighter or Mortal Kombat, and you can actually really practice martial arts, and the better you get, the more energy it subtracts from your opponent and things like that. And here we just continued with a new data set. A student whom I also partially supervising, Gregor Endler, just started to record 5 to 6 new students with also some new magnetic field sensors, and we hope to publish something also in this aspect. So moving over to now away from this application scenario, so you saw, you know, from healthcare over industry to sports. There's a lot that can be done. More towards the enabling technologies, and as you might have also realized, variable computing or Ubicomp or pervasive is a very interdisciplinary field. So usually you know, you have the traditional embedded systems in there, and usually what we do, we pick the sensors, you record some data, you do some offline processing with MATLAB or SciPy or some similar tool that is really good for number crunching. Then you apply some machine learning, maybe also beforehand some signal processing techniques to do the recognition. And then later on, to really implement the system, you have to do a switch. You have to go to a real embedded platform, and this means usually re-implementing everything from scratch. And some effort to overcome this problem is basically the PhD thesis from David Banach. He focuses on the context recognition network toolbox. This is supposed to be an environment that allows rapid prototyping for context recognition systems, and all of our demonstrators and all of my data collection, so for Kung Fu or other things, basically use this platform to either record data or also do data to classify. And some of the straightforward features are that the toolbox is data flow oriented. This means basically on the top you have your readers, your sensor readers, accelerometer reader or similar, and then you apply some filters, some intermediate steps, some classifier onto it, and then also some output device. You concatenate them and can do basically the classification. It's component based, it supports synchronization and other things. For the toolbox itself, it's open sourced, LGPL, it's written in C++. Okay, not really my favorite language, but David tries to keep it quite clean. And it requires the only thing it requires is POSIX threads, so it runs on a multitude of platforms. We have it running on the Nokia N8010 and also on an iPhone, iPod Touch platform and so on. So it's available open source, as I said, from SourceForge. You can check it out. However, small disclaimer, this is kind of research software, so the documentation might not be as good. As I said, a lot of people, actually our whole lab and also the lab at ETH basically uses this toolbox to do data recordings and also to build classifiers or demonstrators. So another thing I want to pitch is a student of mine just started 1 month into his diploma thesis and wrote a little context locker application for the iPod Touch and iPhone. Unfortunately, it's not yet on the App Store because, yeah, it didn't get accepted yet. But we hope that it'll be in mid of end of January. And what you can do there, it's basically just the start of his diploma thesis. You can basically just select some labels. You can specify some labels. Nothing, walking, running, hand wave, stairs up, stairs down, and then they get shown on the recording view. You can start a recording, press a label, record some accelerometer data, and what you get then later on over a web server that runs on the device is a file where you have the timestamp, the accelerometer data, and the label in it. So basically how this would work is I select the label, I start the recording view, start a recording, press hand wave, do this, stop the recording, and then I can basically take a look at how hand waving or so on looks like, and you can get a feeling on how accelerometer data actually looks for different gestures you do and so on. So this might be just useful for researchers or really people that are extremely interested in this, but there's more to come. So he's just 1 month into it, and yeah, I'm looking actually forward to. We have some nice ideas, I hope. Okay, now moving over from the enabling technologies towards some of the issues and problems activity recognition faces today. And as you could see from some of the movies and also from these pictures, this is not really practical for everyday life because some of the setups take up to 40 to 50 minutes to actually get the person dressed into the sensor garment. You use usually a fixed location for the sensor, fixed orientation. The algorithm works just in case if you have the sensor oriented like this, and if it turns, it won't work anymore. And you use dedicated sensors, so if a sensor fails, sometimes your classification doesn't work. And so one of the pretty obvious ideas is to get over the dedicated sensors, basically to use off-the-shelf devices that have sensors embedded in them, but then you have to deal with all sorts of different problems, as you can imagine. And this is kind of also the work I'm basically doing for my PhD. So I just try to tackle several small problems of these huge ones. So first thing, if you use devices that are not dedicated sensors, you might not know if they're on the body, and if they're on the body, you don't know the on-body location. So I did some work on trying to detect the on-body location using accelerometers, and also if you know the body location or the segment, you might have a sensor integrated into your sleeve. If you pull up the sleeve, it changes and displaces. So I did some work on placement on the body segment, and some other work I did, and we will go into more detail in a second. In this one is basically if you don't have it on the body, it's somewhere in the environment, and usually normal people don't care about X, Y, Z values or longitude or latitude values, but more about symbolic or semantic location. So is it on a chair or is it on a desk or something like that? And we look at this in a very specific example, actually with a mobile phone. And basically what I used there is something all of you are familiar with. If your mobile phone lies on different surfaces, the vibration sounds different. So, I'm not sure if I haven't sound plugged in, but I hope maybe you can hear it. Can you hear it? Okay, so this is the cupboard. This is the chair, and this is then a metal compartment. so people can recognize on which surfaces they lie. So basically we use this principle, and what you can do with, actually this started out with me getting a new mobile phone 2 years ago or so on. It was one of the Nokia 5500 Sport. The nice thing about it is you don't need to use Symbian C or C++ to program for it. You can just use Python, and it's a really nice scripting experience on the phone, and you can let it vibrate, you can record data on it, and so on. So basically I played around with it, and what you can do is you can sample acceleration and sound signatures. So you can play either a sound fingerprint over it had an MP3 player, a speaker included, so you can play a sound fingerprint and then sample the sound back. So you basically get a frequency response from the surface the device is on, or you can activate the vibration motor and then sample the acceleration and the sound. And then you get some idea basically where it lies. This is, by the way, published at Ubicom 2007. A paper, if you're interested in the machine learning aspects and so on. I will just show you some signal level examples now. So for the vibration acceleration, so if you let it vibrate on your home stereo or on your bed, the norm of the acceleration sensor, so the magnitude of the intensity of the acceleration sensor definitely looks different. So you see there are different patterns in there. And also if we go into the audio data, so these are the fingerprints for vibration. You see here frequency, so slotted FFT over time here. Down here is the vibration for desk, and down here is the vibration for carpet. You directly see the difference. And also on top here I use this this audio fingerprint, so basically playing distinct frequency chirps in different in different frequencies, so from 500 till 3,500 hertz. This was kind of the range the mobile phone could do over the speaker. And then you also see here the frequency response for desk and carpet definitely looks different. So you get some resonance in the 300 hertz chirp, for example. And using this and standard machine learning, I have one disclaimer here. Of course, this is done batch processing with MATLAB scripts and SciPy scripts. Nothing actually runs on the device currently. It still uses some heavy frequency domain features. So basically, two modes. You can use you can use these features or these frequency response. You can use it on first pre-trained locations. This means you train it on a certain desk, on a certain chair, and so on. I picked around 30 locations in my home, and then you basically get the result. Okay, your phone is on the office desk. If you then ask the classifier, or even more interesting, this means that you would first you buy such a device, and then you have to sample each location in your home where you might put it, which might not be so practical, but it gives the better results. You can also train it on abstract classes, something like padding, glass, surface, metal, stone, wood. For this I went to a furniture store and basically tried out all kinds of devices. Yeah, the weird thing is nobody asked me what I was doing with the mobile phone. Everybody was interested in the laptop. I had 10 or 15 people asking me why I'm here with a laptop, but nobody cared about the mobile phone beeping on the surfaces or on the tables and so on. Yeah, and then you get basically a result like the phone is in a closed wooden compartment, but yeah, you might then yourself need to look for the closed wooden compartment. Okay, this so far to the opportunistic sensing. Now, as I promised at the beginning, over to the more general issues. Here I first want to address the practicality. And as you might guess, this is something I hear a lot. Yeah, it's interesting, and there are some nice approaches in there, and yeah, fascinating research, but is it really useful for normal people? And to address this question, we actually did an experiment in maintenance scenario. This was work also where at Here at Work project with Zeiss in this case, with Erson Kattal from Zeiss and Ernesto Kluge Morales from BIBA Bremen, University Bremen, and Florian Wagner, a student who also works for our lab. And basically what we did there, we tried to assess, how useful are, in this case, especially heads-up displays and some way of context or error correction for maintenance workers. And so we picked the coordinate measuring machine at Zeiss and 3 maintenance tasks for this machine. 18 participants. From these 18, none of them were volunteers, so Zeiss supplied us with 18 technicians, skilled technicians. The tasks are, not something I could do even now after seeing it, 3 times, 18 times. And we basically gave them 3 utilities to do the maintenance tasks. One was paper, one was speech, and one was context. I go into detail later what this means. But we used the Wizard of Oz approach. This means that we actually didn't really implement an activity sensing system, but we simulated it. So, we had our rules, and then basically pressed the right buttons for the rules. You have to be sure that, it's something that not only a human can detect, but a computer can detect, and we really tried to do this and really oriented ourselves on related work and also work we did in our field to make sure that we don't implement something that is not feasible in real world. For the experimental setup, here you see this coordinate measuring machine. The test subject then basically, in this case, he had a heads-up display from Zeiss. If you want to try it out, I have one here later on or so on. It looks a little bit clunky, but the nice thing is it's actually the first heads-up display I used that, as I said, it looks a little bit weird and clunky, but it's the first heads-up display I used that didn't give me headaches. I mean, I used several of those, and so micro-optical, for example, looks a bit sleek and nicer because you can just attach it to your glasses, but I couldn't use it for longer than 20-30 minutes because after looking at the screen, I feel nauseated, and this has a really, really good quality. And it was not really done for the experiments. We wanted to use actually prototype from mobile optics, but due to practicality reasons we couldn't. So we have the test subject wearing the glasses. We basically just have a VGA cable connected to the glasses, and down here a laptop where, in this case, Florian can basically steer what the technician can see, and another display for the coordinator of the experiment to actually check what the test subject or what a technician actually sees. 2 ways for ground truth. One is a video camera we filmed this with, and also an active marker system, an active infrared marker system you see here, and you see the technician wears some tags on the arm, so we can basically localize what he did during his work. And as I said, we gave them 3 utilities to fulfill the task at hand. One was, the good old paper manual. In this case, as the paper manual for maintenance for this machine is around 500 to 600 pages, we slimmed it down a bit. So that is actually usable, and we used then this version where we just basically compiled all the steps that are somewhere scattered in this manual. We used this to then build the display device, and the other modality they had, or utility had, was basically speech recognition, so emulated speech recognition. They could just, this is a sample of the screenshot from what a technician would see on the screen. If you wonder about the colors, they are picked because they give the best contrast ratio on the heads-up display, and it's very basic. So what you get is just the information that is also in the paper manual, the picture, the tool you should use, and what you should basically do. And on the top, he has a progress bar to know how far he is in the step. And he can basically use speech detection and quotation marks, so he can say previous or next to step through the single steps. And in addition to this, so this was one, paper, speech. The third was then context. With context, we added this bar, and this is an error correction bar. So basically, we defined up front some errors that might happen. One of them is, for example, touching the bearing surface. This is he's a step ahead. He forgot something. This is using the wrong tool, and so on. And if then an error happens, and we defined it as such on the list, this was quite some tough work to always agree on what kind of error happens, because you also want to give fast feedback to the technician. Then you get something like this, and then the technician gets a warning, basically that some of the task steps are wrong. And as I said before, so this is the Wizard of Oz GUI. We're currently trying to open source it. There's no source code available yet, but should be in a couple of weeks. So basically, you can control each step, you can control the errors that are displayed, and so on. And now moving over, we did this now for 3 times 18, so for each participant basically did each of the maintenance tasks with another modality. And now for the results, quantitative, oh yeah, another thing, this is not published yet, so you are the first ones to hear about this. This is kind of, it's accepted for publication in April 2009 at Pervasive. Just wanted to mention that. And quantitative, nothing too surprising, so context is basically the fastest modality to use. It's 30% faster than speech, and 50% faster than paper, and also statistically significant. But more interesting, we dealt with this problem of are such systems useful, or would normal, in quotation marks, people use them? And over here you see a question from the question mark, from the questionnaire. Basically, the technicians got asked if they would like to wear the system in everyday work. And as I said, there were no volunteers, so no tech-savvy people that tried the systems, but technicians that basically just wanted to get their work done. And 13 said yes, they really would like to have such a system at work, and just 1 said no. 4 were indifferent about it, but the one who actually said no had specific contact lenses and couldn't see the display very well. So, and even more overwhelming is which modality did you dislike the most? And there were kind of 17 with paper, so they didn't like the paper manuals they had now, and just the one that actually had problem to see the display at context and speech. So at least for this maintenance scenario, for this limited set, we can say that if implemented correctly and supporting the users in a decent way, it's useful. It can really make a difference. Now moving over to the last general issue I want to tackle, this is privacy. And the first point I have to make, of course, all this technology is basically, if I wear a sensor on my body, I give away a lot of intimate information about myself, and everybody has to be clear about this. But on the other hand, there ain't such a thing as a free lunch. So, if I want to use a specific service, if I want to use a mobile phone, I have to live with that I can be traced or tracked. Or if I use a credit card, I also know the dangers and perils. But this is also the second point I want to make, and this is actually also the reason why I'm here today, and so on, just to raise awareness, because I think a lot of people are not really aware of what such a little MEMS chip integrated in their mobile phone or so on can actually mean for them. What kind of information can you actually data mine from such low low-level sensors. And the last point for this is kind of then awareness and basically also telling people what the trade-off is. If you use this technology, you have to live with that this information gets out. And then also 3, making Big Brother smaller. This basically just means to help people make the right decisions for the right systems that preserves maybe a little bit more their privacy than another system would. And here a small example or a small idea we had while Gerald Bauer, another PhD student in our lab, was working for the Mon Ami project. This is a project that cares about elderly and elderly home care. So the idea is keep the last puzzle piece with you. So basically, all these wearable computing technologies and so on work with inferring some state, using machine learning techniques. And do the last bit of reasoning, the important bit, on the local device of the user. This is something that might be implemented. It won't work for all the systems, but it might work for some. And what you see here, this is a combination of camera tracking, and the camera just gives away, this green circle. It doesn't store any IDs of a person. It does not try to put any, to identify any of the persons. Basically, it just gives you away this green circle. Then you have maybe a mobile phone with an accelerometer inside. You can access the service of the camera that gives you this green circle with some velocity to it, and then you correlate the accelerometer on your local device with the green dots, and then you basically know which dot you are and get your location without losing your privacy. And so this is one example. So you see iPhone activity is on 1 and camera activity is also on 1. Then Gerald stops, and then you see, okay, camera activity goes to 0, and also the iPhone activity goes to 0. And if he moves, the iPhone activity stays on. And if he goes out of the area where the camera is, of course, the camera activity goes to 0. So of course, this won't solve all of our privacy problems and so on with this technology, but it might be a help or a hint for people that try to design those systems. And that actually also brings me to the end of the presentation. Here the links of our institute. If you're interested in the machine learning aspect and how to really build those systems, we have also a wiki in place where I put some tutorials from a course I also teach, Intelligent Technical Systems. You can step through the tutorials and actually see how to really build such systems and how to combine signal processing, machine learning, AI techniques to build them. Of course, you can get our toolbox, or also you get in touch with me if you have, or also now if you have now any questions, remarks, violent dissent. Yeah. Thanks. Do we have a microphone for the? Yeah.
Can you buy the glasses?
The glasses. The question was if you can buy the glasses. Actually, you could buy the glasses, but currently the state of, as far as I know, the state of mobile optics, Zeiss, is unknown. They wanted to basically stop the whole department, and now there's some discussion about it. I hope that this is resolved and they continue the production. You could buy them, you might be able to find them somewhere. They were actually produced for medical applications. Yeah. Some more questions?
Yeah, does the color vary? Because that's why the color is
what and if the color varies,
because that's what that determines
The color varies from the display here. Yes, it does a bit, but not that much. I mean, it depends on the problem. There is depending on what color you use. You have to live with the problem with these displays is that if you get too close to the eye, you have this issue that you cannot focus. So they play little tricks, and depending on what colors you use, you get ghost images. So if you use, in this case, if you use black on white, the contrast ratio is alright, but you get a ghost image of the written text just behind it somewhere, so you cannot really read it. That's the trouble with the displays. So you always have to be a bit careful to choose the right color. It can affect different eyes.
The headaches, people get headaches.
Ah, right. Yeah.
That's something that maybe you should.
Yeah, right. Yeah,
Do you work with the materials connections?
a little bit. People at ETH do, but okay. No.